Swayam Prabha. Digital India. Educated India.
Welcome to the 22nd lecture in our particle characterization course. In the last few lectures, we have dealt with aspects of particle interaction with its surroundings, interfacial properties such as particle adhesion, removal from surfaces, particle cohesion, and so on. Starting with this lecture, we are going to deal with the fourth aspect of particle characterization. If you recall in the earlier lectures, I mentioned that particle characterization, at least in the context of this course, can be classified into a few major categories. We started with morphological characterization, which was shape and size related. Then we talked about structural characterization, and the third aspect that we have dealt with is actually the interfacial characterization of how essentially a static particle interacts with its nearest neighbors. In starting with this lecture, we are going to discuss the fourth aspect of particle characterization, which is transport properties. It is important to know how particles behave in a dynamic mode, because particles that are suspended in fluids have a natural tendency to move around. They are not going to stay in place. Unlike a large object, I mean, you look at something like a table, it stays where it is. But if you keep breaking it up into smaller and smaller fragments, eventually you will reach a size which is not static anymore. It has a tendency to move in response to the motion of the fluid around it, or when the particles get to be sufficiently small, they will move on their own without the need of an external force field being applied. And the dynamic characteristics of particles again play a huge role in industry. You have to learn how to predict, how to control, and how to manipulate the movement of particles in order to derive the maximum benefit from your particular technology, whatever it is. So when we talk about transport characteristics of particles, as we have briefly touched upon in the past, the predominance of the transport mode depends very much on the size of the particle. So when we talk about extremely small particles that are in the submicron range, the dominant mode of transport is diffusion, which in the case of particles goes by the name of Brownian diffusion. In the very fine particle size range, electrostatic effects are also important. Now, as particles become a little larger and you start approaching the micron to a few microns, 1 to I would say around 10 microns, then essentially the convective motion of the particle becomes the dominant effect in dictating how well the particles move around in a system. So in this size range, convection, drag become important forces, and here we are talking about forced convection as well as natural convection. And of course, drag can happen in the very low Reynolds number range or in a higher Reynolds number range, but all of these are particularly applicable to particles that are in an intermediate size range. Now, as particle sizes start exceeding the 10 micron range, inertial effects begin to dominate. So very simply put, the transition in terms of the dominant transport mode evolves in this fashion from diffusion and electrostatic to convection and drag to inertial effects. So, in order to understand how particles move, we really have to take each of these and look at them in a little more detail. So, we will start with diffusion. Now, I am sure you are all familiar with thick diffusion of vapor molecules, and it happens by what is known as a random walk process. When two adjacent molecules hit each other, they exchange energy and they rebound and move in different directions. So, essentially as a molecule encounters an adjacent molecule, there is a correction in its trajectory and it goes towards a new place. Now, when we talk about particle diffusion, what is the difference? A particle in the case of diffusion can be considered just like a heavy molecule. The interactions are very similar, but here one of the key things we need to focus on is when you have a particle, by definition it is a little larger than the vapor molecules or fluid molecules that are surrounding it, and so you have all these molecules that are surrounding the particle, and the particle is being repeatedly impacted by the surrounding molecules. As that happens, there is an imbalance in the momentum that develops. So, if there is a preferential direction in which more collisions happen, and so that transfer of momentum happens to a larger extent in one direction compared to the others, the particle will have a tendency to move in that direction. It is still a random walk phenomenon because the collisions that are happening are essentially stochastic in nature. However, there is a net movement of the particle due to these collisions of the molecules surrounding it, just like in the case of thick diffusion, there is a net movement of the molecule because of the collisions that it undergoes. And that distance in the case of thick diffusion is given by 2 times dt, where d is the thick diffusivity of the molecules, the thick diffusion coefficient. In the case of particle diffusion or Brownian diffusion, the same formula holds, except that now you substitute the diffusivity parameter with the one corresponding to a particle. So, these equations basically say that the particles will experience a net movement due to these repeated and random collisions, and it goes as the square root of both the diffusivity as well as the time over which the diffusion process is occurring. The particle diffusivity itself is defined by 2 kT Cc over 3 pi eta dP, where Ka is the Boltzmann's constant, T is the temperature. Again, the Cc factor is the Stokes-Cunningham slip correction factor. Now, this correction factor essentially accounts for the fact that we always assume continuum, right. Now, the continuum assumption tends to break down to some extent at the interface between a particle and a molecule, or at the interface between two molecules. So, even though the fluid system as a whole may be in continuum flow, again the definition of continuum is a very small Knudsen number, where the Knudsen number is the ratio of what the mean free path to the particle diameter, right. Now, in general most flows that we encounter do satisfy the continuum condition. However, there is a slip between the particle and surrounding molecules, or between one molecule and the molecule around it, which violates the continuum assumption. And in fact, at the interface what you have is what is known as free molecular flow rather than continuum flow. So this CC is a factor that has been developed essentially to correct for the fact that the continuum assumption is violated at the interface between the particle and the molecule, and it is equal to 1 plus a function of lambda over dp, where lambda is the prevailing mean free path and dp is the particle diameter. So this correction factor increases rapidly as particle diameter drops. In fact, this factor Cc will tend towards 1 for dp values that are in excess of 1 micron, but the Cc values can be much larger than 1 as dp drops below a micron. For example, in the case of particle diffusion in air, let us say you are at atmospheric pressure 20 to 25 degrees centigrade, the mean free path for air under those conditions at 1 atmosphere 20 degrees centigrade is about 0.066 micrometer. And under these conditions it turns out that you can write Cc as equal to 1 plus 0.16 over dp, where the particle diameter is expressed in microns. So what is the implication of this? When dp is, let us say, 10 microns, Cc is approximately 1, because this correction factor is 0.01, right, less than 2%. When dp is equal to 1 micron, Cc is about 1.16. So there is a 16% correction in or there is a the Cc value here, instead of being 1 is now going to be 1.16. So in terms of the diffusion coefficient, what does it mean? It increases the diffusion coefficient by 16% compared to if you had neglected this slip correction factor. And of course, if this drops further, if dp drops to 0.1, then the Cc value now becomes 2.6, and if it drops to 0.01 or 10 nanometers, this correction factor is as large as 16, so this becomes 17. So you can imagine that as the particle size drops, the slip correction factor begins to gain in significance, and the practical implication of that is, again, if you re-examine the diffusivity value, it is proportional to temperature, as you would expect. As temperature increases, diffusion is faster, everything moves around more quickly. Viscosity is in the denominator, diffusion happens faster in a less viscous fluid. The particle diameter is also in the denominator. However, when Cc values are small, or when particle diameters are large, there is only a 1 over dp relationship between the Brownian diffusivity and particle diameter. But as the particle size becomes smaller and smaller, the Cc value essentially becomes proportional to 1 over dp. So what that does is dp value then becomes proportional to 1 over dp squared for particles in the submicron range. Now that is an important consideration, that dp will go as 1 over dp when dp values are of the order of 1 micron, but it will go as 1 over dp squared when dp values begin to drop well below 1 micron. So the inverse dependence of diffusivity on size becomes exacerbated as particle sizes become smaller and smaller, and also for a given particle diameter, the value of the Brownian diffusivity is much greater than you would have predicted based on the continuum assumption alone, as the diameters again drop below 1 towards the nanometer sizes. So, very important to keep in mind this correction factor for the slip between the particle and the surrounding molecules. Now, let us get back to our discussion of Brownian diffusion. So, we have said that essentially the distance that the particle moves once you have calculated the Brownian diffusivity dP will be equal to square root of 2 times dP times T. What is Fick's first law of diffusion? Anybody knows? It relates flux to gradient, right? So, similarly for particles also there is a first law of diffusion, which basically would say that if you look at the particle flux, transport flux due to diffusion, let us call that some MP dot double prime, where P represents the particle, the dot represents per unit time, and the double prime represents per unit area. So, MP dot double prime represents mass of particles transported per unit time per unit area, which is the definition of mass flux, right. So, the Fick's law as extended to particles would basically say that this is proportional to gradient in omega p, where omega p is the mass fraction of the particle, right. According to the Fick's diffusion law, flux always happens down a concentration gradient and it is proportional to the concentration gradient. In its full form, you can write this as MP dot double prime equals dP times rho times gradient in omega p, where dP is again the Brownian diffusivity, rho is the density of the surrounding fluid, and gradient in omega p is the mass fraction gradient that drives the diffusion process. By the way, there is usually a negative sign associated with it because diffusion is conventionally regarded as occurring towards the control volume. We will discuss those aspects in more detail later on, but for the time being just look at how particle flux is related to the diffusivity parameter, the density of the fluid, and the gradient in the mass fraction. Now, this law is applicable under what conditions? What is the basic assumption here? Among many, one of the assumptions is essentially it is a steady state process, right. You are assuming here that you are essentially have achieved a steady state gradient in the mass fraction, and there is a flux associated with it which is also occurring in a steady or quasi steady manner. The second law of diffusion accounts for the time dependence, right. Are you familiar with the second law of Fick diffusion? The Fick's second law of diffusion dictates how or the time dependence of molecular diffusion, and again there is a corresponding second law of diffusion for particle diffusion, which says J equals N0 times dP over pi t to the power half, where N0 is the number of particles per unit volume far away from a surface. By the way, one of the things you have to consider is why does flux even happen? I mean, why does mass diffuse in a certain direction? It is because you establish a gradient in that direction, right. But how does the gradient get established? If you have a free flowing fluid and you are assuming that particle movement is completely random, then in theory there should not be a gradient, right. essentially the concentration should be roughly uniform everywhere if concentration distribution is occurring only through diffusion processes. So what leads to a gradient? Well, actually if you are just looking at the flow of a fluid in a free volume, diffusional phenomena are virtually absent due to concentration gradients alone. Diffusion still happens because of other factors such as thermal gradients or other energy gradients, but not to a significant extent based on a mass gradient. However, when you look at a surface over which a fluid is flowing, under these conditions mass flux due to a concentration gradient becomes highly likely. What is the reason for that? The reason is that the fluid molecules that are adjacent to the surface have a tendency to strike the surface and get attached to them, right? And similarly, particles that are flowing adjacent to the surface have a tendency to touch the surface, develop an adhesive force, and thereby become attached to the surface. So what does that create? It creates a concentration gradient because you have a large number of particles in the mainstream or far away from the surface, but you have fewer particles in the gas phase or in the fluid phase adjacent to the surface, and that's what's setting up your concentration gradient and initiating your diffusion process. So N0 then represents the number concentration of particles, number per unit volume far from the surface, that is in the mainstream of fluid flow, and dP again is Brownian diffusivity, and T is time. What is J? Look at the units. N0 is per meter cubed, dP is meter squared per second, T is second to the power half. So this is basically 1 over meter cubed times meters per second, which is again a flux term, right? So this J is the number flux. It's not the mass flux, but the flux in terms of number of particles that are transported towards a surface per unit area of the surface per unit time. So if you take this J value and you integrate it over time, you will get the rate of deposition, right? So let's take N of T as being equal to integral 0 to T N0 dt. So this is the number per time, sorry, number per area that has accumulated over a certain period of time from 0 to T. So what would this be? If you go back and do this integration, this is 2 times N0 times dP T over pi to the power half, right? And so the number concentration on the surface per unit area essentially scales as these parameters. Now what is the implication of this formula? Suppose you have an industrial problem where you have a surface that is exposed to the flow of a fluid and you are trying to minimize deposition of the particles onto the surface. It happens very frequently. For example, this may be the product gases from coal combustion in a power plant, and these may be your heat exchanger tubes. You don't want ash particles, for example, to deposit on the heat exchanger tubes and thereby reduce the efficiency of heat transfer. So you want to minimize ash particle deposition by diffusion. Or this could be something happening in a clean room where you're trying to make a microelectronic product and you have contaminant particles floating around in the clean room air, and again you want to minimize the deposition of these contaminants onto the surface. How do you do that? This equation actually gives you a lot of clues. If you want to minimize N of T, you can reduce N0. In other words, reduce the inventory of particles to begin with. If you have a clean room, design the clean room so that you minimize the number of particles that can enter the clean room, and you design your equipment and processes and workstations in such a way that generation of particles is also minimized. So by a combination of these strategies, you can reduce N0, and that has a direct relationship because N of T is proportional to N0. So any reduction that you make in the number concentration of particles far away from the surface will have a direct influence on reducing the number concentration of particles depositing on the surface. The second strategy is to reduce T. Now what do you mean by reducing time? Deposition of particles on a surface only occurs during the time period where the surface is open to the environment. So if I am making an integrated circuit and I want to keep it as clean as possible, then I would only expose it to the clean room environment for as short a time as possible, and then as soon as the necessary processing is done, I will cover it with something, putting it inside a wafer carrier that has a good sealing lid and so on. You can actually protect the surface from being exposed to the surrounding environment. So you try to control T, minimize T. Another way to think about this is, if I am running a manufacturing process which is contamination sensitive, I don't want to build up WIP. Have you heard of WIP? WIP stands for work in progress. In manufacturing, there is something called CFM, continuous flow manufacturing, where you essentially use a pull strategy as it's known. So basically you don't build up inventory at every stage of your process. The end of the line tells you I'm now ready to make a product, so it pulls components. So once you receive that signal, then you start sending material through your process, and you do it in a fashion where it's a continuous flow, which means there is minimum time of waiting for components to be assembled in the next stage of the process. And what you are minimizing then is what's called work in progress, or WIP. So you don't have components just sitting around in a room for a long period of time waiting for somebody to use them to build a product. It's also known as just-in-time manufacturing. The components are delivered to the process just in time, just when you are ready to use them. So this combination of CFM, just-in-time, WIP minimization, all these strategies are good from a manufacturability viewpoint. If you talk to a manufacturing engineer, the first things that they'll preach to you is these aspects of efficient manufacturing. But it turns out that they also have very positive implications for minimizing the accumulation of contaminants on the surface, because they have a direct influence on time T. Of course, the other factor where you have some control is dP. So how do you minimize flux using dP as a controllable parameter? Well, you reduce dP, you reduce diffusional flux. Actually, you basically will want to, what you want to do is minimize the diffusivity of the particle. How do you do that? By having larger particles in your system. But is that a smart strategy? As particles become larger, yes, the diffusion rates will slow down, but all these other transport mechanisms will start kicking in, right? So you may be reducing some of your diffusional fluxes, but at the cost of increasing your convective fluxes, your inertial fluxes, and so on. So you have to think about it in a more systemic fashion. So actually it turns out there is an optimum size range of particles which will actually minimize the overall deposition. That optimum size range though varies from application to application. It also depends on product sensitivities. If you have a product that is very, very sensitive, let's say to submicron particles, then this is a good strategy to minimize diffusion, because even though that might increase the mass flux of larger particles by the other transport mechanisms, they don't affect your product, so you don't care. So you really have to understand the sensitivities of the product you are manufacturing, whether it's a microelectronic product or it's a pharma product, or whether it's a fertilizer or whether it's a food product, it doesn't matter. You have to understand is your product sensitive to particles, and if so, what is the size range of particles that it is most sensitive to? And the way you try to control the transport mechanisms that are present in your system is by essentially adopting an appropriate strategy. You cannot minimize everything. Well, you can, but it's going to cost you so much, your product becomes economically unviable, right? So you have to have a practical strategy that says you don't try to get to 0 particles in your product, but you try to have an optimum control strategy where you try to identify the most sensitive particle sizes, and you have the maximum containment in those size ranges, and for the less sensitive particle size ranges you don't worry about it so much, okay? So it's a combination of strategies that you need to evolve by keeping in mind the a holistic picture of what your product requirements are. Okay, so we have discussed diffusion. By the way, there are other types of diffusive phenomena such as thermal diffusion, which we will talk about later in this course, but the next most predominant mode of transport for fine particles is electrically induced motion. Now electrostatic forces are important because all particles on earth carry a charge. Now the charges may be large or they may be small, but every particle does carry a charge, and that happens because essentially in cosmos you have ions that are present, and essentially when these particles collide with any molecules in air, they pick up charge. Now if the charging of the particles is essentially happening by a random mechanism of collision with ions that are present in the atmosphere, then the charge distribution follows a Boltzmann distribution. So the net charge on a assembly or collection of particles may be 0. However, the individual particles will carry positive and negative charges depending on what ions or electrons they have collided with. On the other hand, if you have intentionally charged a set of particles, obviously they will not have a Boltzmann distribution. I mean, they won't have an equilibrium distribution that essentially results in a net 0 value, but they will have an overall positive charge or overall negative charge depending on the charging field that you have applied to the particles. Now under these conditions you set up a force which we have actually looked at in the context of particle to surface interactions, and that is the Coulombic force. So if you have two particles and let us say they have sizes dp1, dp2, and they have, the first particle has n charges, n1 charges, the second particle has n2 charges, of course each charge unit is E, then the Coulombic force of interaction between them, which is equal to q1 q2 over 4 pi epsilon r epsilon 0 s squared, can be written as n1 E times n2 E divided by the denominator. S squared, of course, S is the distance of separation between the particles. Now if you look at this equation, n1 and n2 are the charges carried by each particle. Now what is the value of n1 and n2, and is there a dependence of charge on size? It turns out that there is a very sensitive dependence of particle charge on particle size. In fact, n is roughly equal to 2.37 times dp to the power half, where dp is expressed in microns. This is the average number of charges carried by a particle which has been exposed essentially to a Boltzmann distribution of charges. And so when you look at this equation, there is clearly a drop in the charge as the size decreases, and therefore if you have two particles n1, the value of n1 and n2 will very much depend on the sizes of the particles. it turns out that even this expression does not fully capture the dependence of number of charges on particle size, because essentially this is if you plot dp versus n, what this is predicting is a square root dependence, which is valid all the way from 0.01 microns to much larger sizes. Actually this is, according to this curve, this should be 0.001, 0.01, 0.11 and so on. If you actually measure charges on particles, it turns out that this slope is much steeper. It actually drops to virtually 0 by the time you get to 10 nanometers in size. So the charging effect in a neutral field is important primarily for particles that are larger than roughly 10 nanometers. If the particle is in the nanometer range, 1 to 10 nanometers, you can kind of ignore charging effects unless there is a charge field that has been induced to deliberately set up a charge on the particles. So this is basically what's predicted by the square root theory, and it actually severely underestimates charge pickup by, or it severely overestimates charge pickup by particles in the very fine size range. So the practical implication of this and what we have discussed about in terms of Fick diffusion or Brownian diffusion is that as you start approaching nano dimensions, diffusive phenomena become much more important than electrostatic phenomena. As you start approaching the 0.01 to 1 micron range, then electrostatic effects become comparable to diffusive effects. As you exceed sizes of 1 micron, the diffusion drops quite rapidly, electrostatic effects drop less rapidly. So electrostatic phenomena continue to play a role beyond a size where diffusion stops being an important phenomenon. Okay, so we have looked at essentially two transport mechanisms that are particularly important for fine particles. As you transition into larger sizes, as I was mentioning earlier, the macroscopic forces that are transferred to the particle by the surrounding fluid start to become increasingly important, and drag forces are among the more important forces that a particle would experience in a larger size range. Now what is drag? Drag is basically a frictional force, right, that a particle experiences as it is traveling through a fluid. Actually it turns out that there are two types of drags. There is form drag and friction drag. What is form drag? Form drag happens because of the particle trying to push molecules out of its way. Friction drag occurs because of the friction between adjacent layers of molecules and the particle as it is traveling. The net drag is actually a combination of both. Now when you look at a drag force on a particle, and let's assume it's a spherical particle, you know that there are two formulations depending on the Reynolds number. I'm sure you have studied this in fluid mechanics. So when the Reynolds number is very small, when Reynolds number is much smaller than 1, you are in the Stokes drag regime. What type of flow is it when Reynolds number is much smaller than 1? It's called creep flow. Whether it's laminar or turbulent depends on the transition Reynolds number. So you can have a high Reynolds number and it can still be laminar flow. However, when the Reynolds number is much smaller than 1, this is called creep flow, and the expression for drag in this limit is Fd equals 3 pi eta V dP by cc, where eta is the viscosity of the fluid, V is the differential velocity between the fluid and the particle, dP is the particle diameter, and cc once again is the Stokes-Cunningham slip correction factor. When Re approaches and exceeds 1, the drag force becomes a drag coefficient multiplied by area by pi dP squared by 4 times half rho g v squared, right. So, CD is the drag coefficient, pi dP squared by 4 is the surface area of the particle, and rho g is the density of the fluid in which the particles are being carried. And the CD parameter has a relationship to the Reynolds number if you plot CD versus RE, what is that going to look like? There is a linear portion, right, and then more of a cyclical behavior. And what is the relationship here? I mean, this is a log-log plot, so this goes from 0.01, 0.1, 1, 10, 100 and so on, and this value is 0.1, 1, 10 and so on. So, in this limit of Reynolds number being less than 0.1, what is the relationship between drag coefficient and Reynolds number? 24 by 24 divided by RE. So, in the low Reynolds number regime, the drag coefficient and the Reynolds number are simply related by CD equals 24 over RE, and for higher Reynolds numbers, the drag coefficient does not drop or increase significantly. What happens in the turbulent regime compared to the laminar regime? Is drag higher or smaller, or you cannot say? Yeah, I mean, in the turbulent regime, all you can say is fluctuations in the Reynolds number do not have a significant effect on the drag force, mainly because in the turbulent regime, the flow itself changes its character, right. You're essentially having a situation where parcels of fluid are being flung about in turbulent eddies. So, it very much depends on, it becomes a probabilistic process. If the object is impacted by several eddies in a period of time, it will experience high drag, but there may be periods of time where, again, given the unpredictable nature of fully turbulent flow, the particle may experience low drag. But if you integrate drag force over time, essentially laminar versus turbulent does not have a significant influence on the drag force that is experienced by the particle. So, when you look at drag force, the expression for drag that we wrote down again contains a lot of useful tips. One of the questions that you always face is, do you want to minimize drag? Again, it depends on the application, right. If this particle is actually, let's say, an airplane that's flying, then you want to minimize drag. So, what would this tell you? Again, if you minimize the viscosity of the fluid, if you minimize the relative velocity, if you minimize the size of the object, whether it's a particle or a plane, that minimizes your drag force. And of course, the Stokes-Cunningham correction factor being in the denominator is something you have to be careful about. It may look apparently like the drag force is proportional to dP, but remember that as particles become smaller, the cc is actually proportional to 1 over dP. So, the actual dependence of drag force on particle size is dP squared for very fine particles. It is not equal to dP. Same as for the case of larger Reynolds number drag, where the drag force is proportional to dp squared. Some of the other dependencies that are interesting are, for example, the linear dependence on velocity in the Stokes flow regime or creep flow regime, as opposed to a v squared dependence at higher velocities. Again, this has practical implications for when you are trying to remove particles from a surface, right. As we discussed in the lectures on particle removal from surfaces, one of the methods that is commonly used to remove particles is to blow air or spray liquid on the surface and thereby induce a drag force. Now, what these expressions tell you is, for higher Reynolds number flows, increase in velocity will have a much more significant effect compared to increasing the velocity of flow in the lower Reynolds number regimes. And in general, if you compare drag in this limit to drag in this limit, which do you think is higher? Is the drag force higher in the small Reynolds number limit or in the higher Reynolds number limit? Yeah, I mean the drag force will increase as you go to higher Reynolds numbers. However, the drag coefficient, as you can see, actually decreases as you go to higher Reynolds numbers until it eventually reaches an asymptotic or a plateau value. Now, what is this drag force usually balanced by? Some kind of a body force, right. So, as the fluid is flowing around the object and exerting drag on it, there is, because the particle or the object is a body, there is a body force that is acting on it, which will essentially balance the drag force. So, that is the gravitational force or the body force in general, which is written as pi dp squared or actually pi dp cubed by 6 times rho p minus rho f times g, right. It's a volumetric force, and this force will, when this force exactly balances drag force for a particle that's entrained in a fluid, what velocity does it reach? Terminal velocity, right, which is a steady state velocity that represents the balance between body force and the drag force. So, we can actually estimate what this terminal velocity is for any object that is immersed in any fluid, and that is the terminal or settling velocity that the particle will reach when it is, for example, dropping through a fluid and being subjected to a body force that pulls it down and a drag force that is trying to resist the motion of the particle under the body force. We will stop the lecture at this point. In the next lecture, we will begin by essentially deriving an expression for the terminal velocity, which will also be used then to establish the inertial force on the particle as the particle size becomes larger. Any questions? Okay, I will see you at the next class.